Hello? Yeah, certainly. And you prefer the microphone over there? All right.
Okay, so can you repeat that?
Brilliant. So thanks. Today I'm going to do basically the problem session accompanying chapter 6, which was roughly what Christoph was talking about the first hour of his lecture today. We've now understood that from Christoph's lecture that noise sensitivity is indeed noise sensitive, and for that we used the BKS theorem, which says that if the sum of the squared influences tends to 0, then the function is indeed noise sensitive. And the version of that theorem that we've actually proved is only that if the sum of the squared influences tends to 0 fast enough, which means fast as a power of n, then the function is noise sensitive. And the function we're looking at in this case is the function of the event of a left-right crossing in a box. Okay. Now I'm gonna try to do this, prove this more hands-on. I'm gonna leave out some details, and there are several points in doing so. One is that you'll see, you'll get some feeling for the calculations and for the methods, and one reason is that we actually get some sort of sharper control on the actual geometry of the spectral, on the Fourier coefficients. So not only what layer they are on, but also some feeling for which kinds of sets have large Fourier coefficients and which have not so large, etc. So this is going to be there's going to be some overlap by this exercise session with what Christoph will discuss in his last lecture on Saturday too, where he will get a very precise estimate of the localization of the spectral mass. So I'll consider the slightly easier case than a rectangular box. I'll consider Tn to be the torus, the two-dimensional torus, and I think well, for the moment I don't really mind whether it's Z2 mod n or if it's the triangular lattice mod n. So the picture is, of course, that you have a square box covered with either the square or the triangular lattice, and that you identify the upper boundary with the lower boundary. You identify the left side with the right side, or if you equivalently want to think about it as a donut. And the event we will consider is that there's a loop winding once around the first coordinate. So an open circuit winding at least once around the first coordinate. Actually, I think I'll call this event, I will call AN, and I might sometimes want to use function notation instead, in which case this is the indicator event of that. There's also, one might ask, and it might not be entirely clear from the definition what we actually mean by this. There's an alternative definition that I might have decided to use instead, but I don't. That's having an open path or an open circuit. Winding once around first coordinate. So far it looks very much the same as that one. But not around the second one. There's some reason I want to introduce both of them. I'll sketch that quickly. I like to draw pictures here for getting some geometric feel for that things might not be entirely trivial. So in this picture, AN is simply the event of going from one point here to the same point over there, and you might well go like something, for example, like this. This is allowed in AN, but this is not allowed in BN. So you understand what the general picture is. Over here on the torus, you of course have this is allowed in both the events, but let's see if I can draw this properly. And I go on the back side, and I come back here and do it like that. This is allowed in the event BN, but not in the event AN. Okay. So the first task is to use RSW to prove that there is some constant, blah, blah, blah. Essentially, we should use RSW to prove that this is a non-trivial event, either of these two, meaning that their probability is bounded away from 0 and 1. Okay, let's go. So maybe I should mention that the reason I'm introducing both these notions is that they're sort of dual to each other. And what do I mean by that? I mean that how can I stop a path going like this? Well, if I have a path going like that, winding once around the second coordinate, then that obviously stops the yellow path, right? Now if I allow the yellow path, if I allow the red path to go like this, then obviously I can't allow the yellow path blocking it to go the same way, because the yellow path could go something like this, right? And they don't block each other. But if I require that the yellow path does not wind around the first coordinate, but only around the second one, then it truly does block the red one. Okay? And of course, dually, if I require the red one to go without using this sort of winding around the second one, then of course I can, any yellow path from top to bottom, from the same point at the top to the same point at the bottom, will do the job. So that's what I mean by AN and BN being dual notions. So by duality, probability of BN is, the event BN is trivially contained in the event AN, but the event AN is blocked by the complementary event of BN, by BN around the second coordinate. So we've got these inequalities. So to prove that AN is a non-trivial event, then we only have to prove that BN is a non-trivial event. Let's see if we can do that. Indeed, it suffices to show that Bn has a probability that's bounded away from 0. Because if Bn is bounded away from 0, then this one is bounded away from both 0 and away from 1. Ideas?
You just build two long rectangles, connect both of them to both sides. The length of the book should be more than.
This sounds like geometry. You should draw a picture. I'll help you. Here's the box. You draw two long rectangles like this. Is that one? Or
No, I mean two long rectangles between those lines. Two long rectangles between those lines overlapping on both sides.
I'm sure you've thought about this properly, but I'm.
Maybe I didn't.
Yeah, and try it. I'm not going to laugh at you. Can't speak for the others, but I won't encourage them to laugh at you.
You take the first one to be, let's say, this, and the second one to be this one. Second one to be this.
Yes. Right, okay. Yeah, so exactly this one continues over there, and then you want to...
And then I want to connect them by two more rectangles. I mean, to connect the... Now I have to cross each of them.
Right, so you require a crossing like this one, and a crossing like that
This
one,
and then I only have to connect
and then you only have to connect them.
with two more. That would be,
Right, by, for example,
yeah,
this vertical box
and another vertical.
and another vertical box. All right. Yeah, that sounds fair enough. That sounds like that would do the trick, right? So the crucial part here is you shouldn't do the trivial, you shouldn't do the, it might be natural that you want to say, obviously connecting the left-hand side to the right-hand side won't suffice, clearly. And you might also be tempted to try and wind the box around itself, so it starts here and then goes all the way and ends back here, or something like that. That certainly won't work because you'll get high correlation between what happens in one and the other. Probably it will work by some elaborate use of FKG or something, but this is nice picture. Okay, so that was the first one. Now this is really a non-trivial event. What's the next thing we want to show? Next thing we want to show is to bound the influences from above, sorry. So we want to prove that indeed the influence of any edge. So now we're in the Z2 model. If we're in the T model, of course, we're having a site here. Of this event, AN, this is bounded by alpha 4 of n halves. Remember, the alpha 4 is the 4-arm exponent in the plane. So this is basically, essentially the same argument as it is in any usual case. Only we have some more. I mean, I forgot to say, but obviously the main point of looking at the torus rather than a box is you add a lot of symmetry. You avoid all the boundary cases because a torus is a surface without a boundary, which is one of its nicest properties. So for a node here to be pivotal, which is, I mean, this is, the influence is obviously the probability of being pivotal. For this one to be pivotal, it would have to have some sort of path winding around it, only maybe missing this point. So maybe it has something that looks like this. Might be a picture. And so it's pivot, but to be pivotal, it also has to have a dual path stopping it, so something that looks like this. So I say that it's bounded by the probability of the four-arm event. Why is that? Well, look, here's 4 arms. Okay. But okay, so we understand basically why there's a 4-arm event going on, right? But what if the point's over here? Well, it's not. This was the box that's centered around the point. You can always choose to cut your torus in such a way that the point is in the exact middle of the box. Okay. So from this should be enough to actually prove noise sensitivity for this AN event. Why is that? Well, because now we've got that the second moment of the influence vector is, what's that? We've got obviously, well, I guess we've got roughly n squared points in our torus. Each of them has influence alpha 4 of n halves, and we proved in the lecture today that that alpha 4 of n halves is equal to n to the minus second moment. So we're squaring the influence here. We're squaring the influence, and we know that the influence has the form n to the minus 1 plus epsilon for some epsilon positive. Of course, if we're in the triangular lattice, we're well aware that this epsilon would be a quarter. But if we're on the even if we're on the Z2 lattice, we've got something like this. So now this gentleman will go to, it will be order of 1 n to the minus 2 epsilon, which does it. So this thing goes to 0, which means that the event is noise sensitive by the BKS theorem in the form we've proved it. Now, the rest of this exercise will be about trying to prove noise sensitivity without BKS. What does that mean? Well, we know a function is noise sensitive if all its mass is sort of pushed away from 0. So for every layer k, the amount of spectral mass at level k tends to 0 as n goes to infinity. That's what we need to prove. I mean, I shouldn't say we need to prove it, we want to prove that for each level k, we want to prove that the energy of this function fn on level k tends to 0 as n goes to infinity. And we know that the we already know this for the first layer, right? Because we remember that of course the energy on the first level is only that's the sum of f hat of k squared and f hat of a singleton for an increasing function. It's crucial that an increasing function is up to constant. Just the influence of k, and we should square that guy. So, since we've shown yeah, that's right. So since we've shown this, we've really shown that the first layer spectral mass goes to 0. Someone told me during the weekend that I should avoid erasing the board so quickly, so sorry. I'll try to stick to that in the future. So the next case we would want to prove is the case k equals 2. And that's going to take some to do, and to do it, we should first need some general facts about Fourier coefficients of 2-element sets of doubletons. So we want to show that the sum over all x and y f hat squared of the doubleton xy. Want to show that this tends to 0. And to this end, we would need like some nice description of, or some sort of upper bound on f hat of a doubleton. So I claim that up to a constant f hat of a doubleton is the probability that they are both pivotal. So I claim that f hat of doubleton xy is bounded from above by a constant, which in this case is 4, times the probability that x and y are both pivotal. I'm not sure if this constant 4 had made it into your version of the exercise sheet. Sorry about that in such case. So this is something that holds for any Boolean function. It doesn't have anything to do with percolation. Now, if I claim this is true, what would be the what would be a natural starting point? What would be the first thing to check? Well, to me, I think the first thing to check would be that this should hold at least for some very easy functions of f, some very easy functions f. For example, functions that really don't depend on anything else than these 2 bits. So first thing is if f is a function of only two variables, then check that this holds. That's not terribly hard. Actually, that's easy, because either there is no point where both are pivotal. If there is no point where both are pivotal, what must the function look like? Well, it must be either constant or a function of only one of the variables. So if there's no point where both are pivotal, then f hat will be 0. If there is a point where both are pivotal, well, then this thing is at least, then it happens with at least a quarter probability. A quarter times 4 is 1, and this is certainly less than 1. Okay. So if f is a function of two variables, then it's trivial, or at least after checking. So what in the higher case? If f depends on more than two variables, then let's write it this way. F of omega equals f, I'll write it like this, f omega hat of x and y, where omega hat equals, this is horrible notation, but you'll manage to understand what I mean. Okay, so if you got a string of bits, then you could of course regard this as a function of that the n minus 2 bits that are not x and y here, they determine a new function which is a function of two variables. And these two are then the input of the new function. Well, what's now from here there's not too much to do, because you can write this. Now what you're curious about, the f hat on that side, f hat of the xy set is just by definition expectation of f omega x of f times x times y. Maybe I'll write omega x times omega y, because these are the actual input variables. And you can if you want to be fancy, you can say that you use Fubini's theorem. And first take expectation over the outer bits, and then take expectation over the two last bits. Of this, which is, of course, just the expectation over omega hat of f sub omega hat of x and y, which is less than or equal to, of course, so this thing is, of course, less than or equal to, by what's over here, 4 times the probability that x and y are pivotal for f sub omega hat. But if they're pivotal for this function, that exactly means that they're pivotal for f, right? Because if you change this means that if you change the values of x and y, then you will change the value of this function, and this function is really exactly the output value of f. you're not quite happy about it. Let's just say that this what are you not happy about?
Expectation. Yeah, I don't quite understand how the expectation is. So the probability that X and Y are typical for F already had, you say that that's just independent of this expectation?
No, it's not. No, it's not. But what you okay, yeah, right. So you divide into two things. Either that. Okay. Basically, what you do is either omega hat itself determines the function. Then your constant, this probability is 0, or it's not constant, and you actually have possibility of X and Y being pivotal for this one, in which case
You can do it as a direct equation. I mean, the expectation is just the sum over all possible configurations.
right.
I mean, this is the same thing.
Exactly. Yeah.
Just the number of cases.
Yeah, maybe this is a nicer way to express it. Right. I mean, what I wanted to point out was that I really make it explicit that you should think of this as once you're looking at two element sets, you should really think of the function as a function of these two elements, and that the other bits just sort of determine what the function is, because that's a convenient way of looking at it. So I don't know if you can hear in the back what people in the front say, but what you can just do is basically divide the probability space by summing over all different outcomes of the other bits. That's essentially what you do. More questions? Otherwise, I want to show you that now bound the probability that X and Y are pivotal points. So thus, after having seen this, that amounts to bounding F hat of two element sets. So here's how I like to write the thing, rather than you have another form in your papers, but by quasi-multiplicativity, that's the same as this thing. Where d is the graph distance between x and y. No, that's not what is that what I wanted? No, that's not what I wanted. I don't want to square that. So this is again, of course, we've seen many times that pivotality has a lot to do with forearm events. This is another, I mean, basically just a special case of that comes in handy over and over in percolation theory. So since we're on the torus, I can choose to center the box pretty much anywhere I want. I choose to center it at the midpoint between x and y. Sounds like a fair idea, right? So x is over here somewhere, and y might be there. Perhaps I want them a little bit closer to see what's really going on.
You can just rotate it and make them on x-axis.
If you feel more comfortable with the x-axis, I could do that for you. Thanks. Now, what does it take for the site x and y to be mutually pivotal? Well, for x to be pivotal, it certainly has to have a forearm event. And I have to have some red cock. Something like this. And for y to be pivotal, it has to have another forearm event. But forearm events don't look like this, do they? Red don't cross white for no reason. So obviously we get some sort of correlation around. I like to picture it like this. I like to picture the box bigger. These are circles. They don't look like circles, but they are. Now, for y to have a forearm event, it certainly must have a forearm event in this box or this circle. For x to have a forearm event, it certainly must have a forearm event here. And for there to be a forearm event out to the boundary of this box whatsoever from these guys, there has to be some sort of forearm event. Going like this. Notice that these things happen in independent domains, right? This circle and the outer part of the box are independent. So the probability of this thing happening is bounded from above by, so I should start by saying probability of x and y both being pivotal, that's bounded above by this probability, since this has to occur. Probability of this is bounded from above, well actually it's equal to big O of 1. Actually, you don't need O of 1. It's just alpha 4 d halves. That's what happens in this box. Alpha 4 of d halves in this box again. So you get squared. And then you have the forearm event from a circle of radius d out to the boundary. So from circle of radius d out to something that's n, distance n halves away from you. Now remember, quasi-multiplicativity says that this is, well, for starters, you might just say that you might replace this by big O of 1 times alpha 4 of d halves, alpha 4 of d, alpha 4 of d n halves. I mean, this is really trivial because I've only replaced this thing by something that's bigger. Indeed, they will be the same up to constant, but let's not worry about that. They're really, so far I really have equality, I mean, trivial inequality. And now what happens? Recall quasi-multiplicativity says that for arm events out to a box times for arm event from that box out to an outer boundary. These multiply up to multiplicative constant. So this is actually the same as ordo of 1 alpha 4 of d halves alpha 4 of n halves. Right. So whatever multiplicative constant I got somewhere. Well, actually, I mean, this thing is harder than the product of these two, so actually I don't even need, for the inequality to go this way, I don't even need to use quasi-multiplicativity, I think. And it's not a big disaster if I would have needed it. Good. Now, what's next? Next, we want to kind of bound this in some way. So what we wanted to bound was the level 2 Fourier mass, the level 2 spectral mass, meaning we want to bound E sub Fn at level 2, which is by definition the sum over all two element sets of f hat squared of xy, which is by this thing 4 is a typical case of big O of 1 times the probability that x and y are pivotal squared. Which is by what we just saw, that's constant times that constant is just another constant, so we get the sum over x and y. There's a sum, obviously. Sum over x and y alpha 4 d halves alpha 4 n halves now try to do some gymnastics with these sums for a little bit before I show you how to do it properly. Before I pretend like I could do it properly without getting lost. I suppose if you want to sum over both x and y, you might as well start summing over y or x, or your favorite. There are n squared choices of x. I mean, yeah, there are n squared choices of x. Alpha 4 of n halves doesn't have to do with x, so that comes out. X or y, and then you sum over all y alpha 4 of d halves, and what's d at this moment? Well, that's d from this point y we're summing over to our distinguished point, which we might as well call origin for the time being. Remember, again, we have full symmetry. This is what makes calculations much nicer, that we can, any point x, we have the the domain around x looks just like the domain around any other points. I lost the square. I always lose the square. I suppose it's there and there and there and there, right? Thanks. So recall that this guy is, we know that that's n to the minus 1 minus epsilon for some positive epsilon. And we square. And then we sum over all y, blah, blah, blah. So now we want to sum over y in a clever way. Here's the origin. Where's y? Well, we kind of need to worry about what y is because we have to take care of the distance from y to the origin. But we only need to do it. We only need to do it so carefully because really, I mean, if we move y by a constant, then the alpha 4 is just going to change by a constant anyway. So let's be happy to consider all y at the same time that are inside a box looking like this. This is 2 to the k minus 1. This is 2 to the k. So I only care where y is situated up to multiples of 2. Up to factors of 2 might be the right word in English. So rather than summing over all y, I sum over all k from 1 to logarithm of n. That's how many boxes of this kind fit into the big box. And how many y are there in this region? Well, there are roughly 2 to the, this is 2 to the k wide, so there's 2 to the 2k in the whole box, and then I overcount the ones in the middle, but that doesn't really matter. So 2 to the 2k times, well, of course, the difference goes into the big O of 1. And then alpha 4 of the distance half, that's something that's smaller than 2 to the k, and I didn't forget the square this time. I guess there's a minus 1. That, of course, won't matter. What's going on now? We've got big O of 1. We've got n to the minus 2 epsilon. We've got this thing is, again, doesn't really matter, I guess, but it's 2 to the we had a square, so 2 to the 2k times 1 plus epsilon with a minus sign. This thing is 2 to the minus 2 epsilon to the k. Now you see why I didn't really worry about the exact things, because this is a geometric sum. The geometric sum will converge, so this is going to go right into that big O1 term we've got there, and we've got just going to be left with this. Yay! There we go. So we've got a upper bound on the level 2 spectral mass of this function. And that's nice. Next question is, what exponent does this actually give to the decay of this thing on the triangular lattice? Remember, on the triangular lattice, we know everything about what the alpha 4 actually is, and we know that alpha 4 is n to the minus 5/4, and so the epsilon I was talking about earlier is quarter, and this is just n to the minus a half. So basically, we've got the spectral mass on level 2 is n to the minus a half. So on the triangular lattice, modulo n times the triangular lattice, we have energy on level 2 is roughly 1 over square root of n. How does this compare with what we knew earlier? Well, what was the spectral mass on level 1? Spectral mass on level 1 was, either you look it up at corollary 6.7, or you just calculate. Energy on level 1 must be, how many points are there? There's n squared points. What's the Fourier coefficient squared? The Fourier coefficient squared is basically just alpha 4 of Aleph 4 is other mathematics. These are things you should not confuse. Alpha 4 of n halves squared. That's, of course, again, n to the 2 to the minus 1 minus epsilon. So this is altogether going to be n minus 2 epsilon, which on the triangular lattice is going to be n to the minus a half. Big O's everywhere. I learned just a few tens of years ago that square root of n and n to the 1/2 are the same. So this is really the same decay rate at level 2 and level 1. Now here comes the question, what do you expect happens on level 3? Suggestions. Would anybody dare to guess that it decays slower than square root of n? That's very good, because there's a there's a pretty deep inequality by Telegram that says that if you decay at one particular rate on level k, then you can't decay too much slower at level k plus 1. Actually, you can only have a logarithmic factor slower. If you don't know that, you should still sort of course, guess that it won't decay slower. It won't either decay faster, though there's no known inequality that tells you that, but actually it'll decay at the same rate. Discuss this. Now why don't you sit down with your neighbor and try to discuss this phenomenon? What do you expect happens for fixed higher values of k? Why don't you discuss that at the same time? Or we'll try to go to the quite hard exercise number 9. So in exercise 9, we should calculate the, we should prove rigorously, or as rigorously as we can, that for any fixed k, layer k, we have a Fourier mass that decays to 0 as n goes to infinity. So as I suppose you can guess, you should go somewhere along the lines of what we've done so far, but I want you to sort of think about where the difficulties may lay before we get started. This is also an opportunity to go through the details of what I just did on the board and sort of try to understand what's magic and what's not. Obviously, the point of this awkward silence is that if it goes on long enough, then you start get bothered with it and realize that it's even better to solve an exercise than to just listen to it. If you've done that, I'm curious to hear any ideas on what may be difficult in the case k equals 3 or k equals large, which wasn't too hard in the k equals 2 case. Let's start from the beginning. The first 3 points of this thing was obviously not dependent on k equals 2, so that's quite all right. What about the fourth one, the one that said that in general for a Boolean function f hat of a 2-element set was bounded by 4 times the probability that x and y are pivotal. Do you expect something like that might happen in the if I replace, or not replace, but rather just insert a z here? F hat of, can it be so that f hat of s perhaps is smaller than the probability that all the elements in S are pivotal up to a constant that's maybe not 4, but that's maybe a constant that depends only on the size of the set S? Would you hold something like that to be plausible? Sean shakes his head. Counterexample? Sorry? Yeah. Exactly. So nothing like this can really, there can't be any real hope that this happens, because I mean, in general, one way of saying this is that in general, for elements of many functions of many variables, it's not likely that any input will have all the bits influential at once. There's always going to be a few guys that are not pivotal, no matter what the input. So I'll have to change this thing. I'll have to change this to an alternative definition, which I call mutually pivotal, where I define the set S is, and then so I'll replace the fact that all elements in S should be pivotal by the fact that the set S should be mutually pivotal, and I'll define what it means. If for any bit in the set, there is an outcome restricted to all the other bits. I mean, we can set all the other bits. We can set all the other bits such that X is pivotal. Now we have to think a bit about what this really means. So I say that mutually pivotal for f and not only for the function f, but for the function f with its input outside of S. Okay, so if you give me a function f and you give me its input outside of f, outside of the set S, then I say that S is mutually pivotal if I go to one bit and I want him to determine the outcome, and I can actually set all the other bits in the set in such a way that this guy is going to be pivotal for the outcome. This may take some getting your hands around this concept, but I'll tell you that this is a key definition to sort of generalize this to higher dimensions. Then obviously, trivially, if f is a function that only depends on these variables on these k variables in S, and it doesn't depend on anything else, but it depends on everything, well then S is clearly going to be mutually pivotal, and you're gonna have, so you can do what we did for the 2-element case here. You won't even need this constant. And then you do the same thing by averaging over all the inputs outside of S to get this. I believe we don't, or I mean, quite sure we don't even need this thing. And even with absolute values there, of course. Okay, so we sort of overcome the problem that seemed to occur in exercise 4. The next thing that might go wrong would be number 5. Number 5 is where we said that, well, that's basically what we did here. We bounded the probability that things are mutually pivotal. So now we have to have something that bounds the probability, that bounds the event that that k guys that may be situated somewhere spread out over the torus, that they are mutually pivotal. Try and draw such a picture for yourselves, if you can. And now, of course, want the balls to be independent, so they got to look something like, I don't know. Notice that this doesn't look too good really, right? Because it seems like you've got a lot of leftover things here. You've got two guys that are reasonably close to each other, so you don't do this too good. So you actually have to bother about pretty large forearm events about from the guys that are far off, and not so large forearm events from the guys that are close together. So if the question was what might go wrong, is not much might go wrong, but it might be a whole lot more technical than it was before. To actually write down the equivalent, of this estimate, alpha 4 n halves, alpha 4 d halves. This is going to look quite nasty in the general case, but you can do it. You can do it for every k. And you're going to get something quite similar. And then there's the next thing that might also go wrong. I'll not even try to argue why it doesn't go wrong, but I again just say that it won't be. Nothing will go wrong. It will just be more technical. That's the dyadic expansion here. So in the earlier case, it was really easy to just pick one boy, centralize the picture around him, and then look at where the next guy is. But in the large, if we have many points, then you of course have to sort of first do a dyadic expansion of where the two closest guys are, and then where the next guy is from them, and then do sort of simultaneous dyadic expansions here and where in the picture. Things will get quite dirty, especially our hands, but you can work it out. And if you can't work it out, you should consult the paper by Gabor Pete and Oded Schramm and Christophe Gabon, which is a beautiful paper, which is what Christophe will talk about in the second to last lecture, where they really do this and to get a really precise, they do it, of course, in the original plane, but the methods are essentially the same, to get a really nice picture of where the spectral mass is actually located. So the point of this exercise was both to avoid BKS to prove noise sensitivity, which I'm not sure I've done because I've weighed my hands at least as much as we did when proving the BKS way, but also to get a feeling for where spectral mass will be located for this function. And for sort of once again emphasizing that working on the torus is a nice sort of smooth place to work and to avoid boundary issues. Although I started a bit late, I guess you want your break, so I'll stop here and I'm happy to answer questions about the rest of the questions. Thank you.